Welcome. In this video, we will develop a conceptual understanding about model calibration, like what do we mean by model calibration, and after we calibrate the model, how could we uh, study the calibration results. Okay, so this is your Facebook activity. So by the end of this video, you should be able to describe the objective of model calibration and the calibration process, and then explain the calibration results of your groundwater flow model. Okay, so basically these are the two objectives for this lesson. Uh, So let's get started and then we will learn more. Yeah, let's do a review first. So these are like the main modeling step. The most important step is to define your model purpose, because that will, once you know the model purpose, then you would know exactly what model do you need and what data do you need and what to be included and what not to include it to answer your question, yeah, management or research question. Then you develop like a conceptual model or multiple conceptual model, which will represent your understanding of this system. And then you select your mathematical model and modeling code. In that uh, particular example, the model we selected is like mod flow developed by the USGS. And Modflow, as I mentioned before, it does not have a graphical user interface. So, or traditionally, it didn't have a free graphical user interface, and we had to use it with Python or with MATLAB, yeah, to just programming, yeah, through programming. But some companies like GMS, Groundwater Modeling System, they develop like a graphical user interface for Modflow family, but it's not free. It requires a license. And USGS also developed one recently. It's called like Model Muse. And in the previous video, we've seen how to use Model Muse to Modflow with GUI, like graphical user interface, like the Model Muse. We saw how to use this to set up and calibrate the model. Yeah. So we did this, like we learned how to use the software, but we didn't understand uh, uh, we just learned the steps. Yeah, so you can do these steps with any software, like with Model Muse. You can do it with GMS, whatever. Yeah, any graphical user interface. That's what we learned at the uh, last lesson. But in this lesson, what I want you to learn or understand is the calibration process. Like, what is what do we mean by model calibration? And like better have a better understanding of individual components of the calibration process. So that's basically the objective of this lesson. Yeah. And then after you calibrate your model, you use your model, and then you develop your modeling report, and then you implement and do post auditing. And then based on implementation and post auditing, you can go back to any of these steps. Yeah. Go back to here, 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 or even go back, change the purpose. Change, like say, maybe this is not important, this models that we develop, and there we can do something else. But anyway, uh, so this is the calibration process. So the calibration is that you set the calibration target. So let's say the calibration target that I want to set is that I don't want, like, I want to calibrate this model for hydraulic head, yeah, for the head. And so there is the head that is simulated by the model, there is the head that is observed in the field, and my calibration target is that I want the difference between these two to be like the residual, like the error, like the residual to be less than or equal, like let's say 10 centimeter, for example. I think for your project, this error, I'm telling you, try to, your term project, try to match the head simulated and the head observation for all your observation. Well, it should be less than 20 or 30 or whatever number, just something like this. So that's the calibration target. And then to achieve this target, you change the parameter of the model. So you keep changing, adjusting the parameter of the model until you achieve this calibration target, like 10 centimeters. The error, the difference between these two at all my observation point is less than 10 centimeters. So what parameter do you change? Like you change the hydraulic conductivity, you change the boundary condition, you change anisotropy, for example. You change recharge, yeah? So you keep adjusting these parameters, and you can do this manually or automatically, like using an optimization algorithm, until like you achieve your calibration target. So you keep changing your parameter until you achieve your calibration target. So uh, if the error like then is unacceptable, then you keep doing this, yeah. So like you check the error. uh, if the error is unacceptable, like you, like if it's error unacceptable, yes or no. So if it is yes, you readjust your parameter, you check the error. The error is unacceptable, yes, then you go, the error is unacceptable, no, it's an acceptable error, then process the result of the calibrated model. So that's what we will learn into this video. Like if your error is acceptable and you're happy with this calibration results, and how to process the results of the model, like to analyze your calibration results and to plot your final head values after with the calibrated model. Uh, and then uncertainty analysis. Like in this course, we don't talk about uncertainty analysis. That's a big topic, but and that's one of my main research focuses. So my two main research focuses in or my two main research focuses is one is groundwater sustainability and the other one is uncertainty analysis. So that's one of my expertise, or at least used to be one of my expertise. I haven't been doing like publishing a lot recently about uncertainty analysis. I use most of my previous publication were on uncertainty analysis. Yeah. My recent publication would be more on groundwater sustainability and this topic, yeah. Because it is, yeah, it was like uncertainty analysis was a big topic like 10 years ago or something. Now, the big topic now is be something different. Yeah, each decade or each 10 years you will find like a new topic which is like the big topic. But and by big topic I mean that's where the funding agency will be have like call for proposals. So they'll have like you'll see a call for proposal for that would address uncertainty, like with topics related to uncertainty analysis. Now, funding agency now call for proposal, like the recent call for proposal would be more on like AI and things like that. Yeah. And more on yeah, more on AI. Okay. But anyway, so let's keep moving forward. So before, like, so in this, what I want you to know in this video, just like develop your conceptual understanding about this topic. So calibrating, like to set up a model is easy. Yeah? So anyone can set up any model, but the difficult part is not to set up the model. Like I can set up a model in an hour. The difficult part is how to calibrate this model, how to make this model match what I'm observing in the field. And that's the difficult part. And so I can set up a model in one day, but I could spend like 2 or 3 or 4 years just calibrating it because If I don't know what's in the subsurface, it's very difficult that my model will reproduce what I'm observing in the field. Like that is like and what I'm observing in the field, that could be like the hydraulic heads, that could be concentration, that could be spring discharge, that could be submarine groundwater discharge. Yeah, that's what I'm observing in the field. But anyway, uh, so here I'm showing you, like, I just want you to differentiate between two things, like a high fidelity model and a complex model. Yeah, so that's these are conceptual understanding. So high fidelity model. So for example, like here, see this example, like you see on the left hand side, like this one here. This is a high fidelity model. Why? High fidelity means it's realistic. It's realistic, is more realistic and more representative of the aquifer in terms, like here, high fidelity with respect to geology, because the geology would look something like this. The geology will not look like these sharp zones. Yeah, would look like more like this smooth transition. Yeah, so this is a high fidelity model because it looks more like, or more representative of the actual like field condition or the actual aquifer. But it is simple model, because why it is simple model? So here, this is like an aquifer, this is a semi-conductive layer, and this is another aquifer, and this is an impermeable layer here. You see, this is like like the actual geology would be more like heterogeneous like this. But why is it simple model? Because let's say I want to calibrate this model, and let's say I only have like the calibration parameters hydraulic conductivity. So I want to change the hydraulic conductivity value here, like let's say, so this is K2. This is like K, like for phases 1, K1, and this is like K3. So I only have three hydraulic conductivity value. And by changing this three hydraulic conductivity value, I want the heads that I'm observing here would match the heads that I'm observing in the field. So this high fidelity, because it's realistic, is simple model because it only has three parameters. While here, if you look at this one, then it's the same, like a different conceptual model, but I was not able to get this like good representation of the subsurface. So I had, like I said, maybe okay, maybe I have one zone here, something like this properly, yeah, and then another zone here, like something like this, and maybe like a third zone here. Maybe I have a fourth zone here, maybe, and the fifth zone here, and another zone here. And maybe there's one more zone here, and that would be like a different zone here. You see, like that's what is caring. And maybe you see here, this one is different than this one, so maybe I have a zone here, and see this one is different than these two. So you keep creating these zones. So this is a low fidelity model because the actual geology is not this sharp zone, but it is complex model because I have 15 parameters that I can play with. So for zone 1, I have like K1, K2, K3, K4, and so on until K15. So here I only have like three parameters. Here I have 15 parameters. So this is a low fidelity geological model. It's not very representative. What is a complex model? Because it has 15 parameters. So so that's like, and if you are like an experienced modeler, you will always try to create like simple models, yeah. And simple model does not and high fidelity simple models, yeah. Simple models mean you only have few parameters to play with. Because if I have many parameters, I could fit anything. Yeah. So if I, the more the number of the parameters that I include, I could just fit anything. Yeah. If I have many parameters. So that's one thing I want you also to know, like two take home messages from this figure. The first figure is calibrating a model. That's the most important task. Like setting up a model, that doesn't mean anything. Yeah. It is calibrating the model. It is when your model is reproducing what you are observing in the field. That what matters. Yeah. And calibration, if you can reduce the number of your calibration task, like make your model simple, that would be always a better model, like a simple model. And simple model does not mean that I mean, that is a simple model because it only has 3 calibration parameters. This is a complex model because it has 15 calibration parameters. So that's what so I want you also to differentiate between the simple and high fidelity or complex and low fidelity. Yeah. Okay, so that's I want you to differentiate this. These are some basic concepts about model calibration, but let's look more at what do we mean by model calibration. So calibration is history matching. So let's read this definition. Calibration is the process of adjusting the model parameter, and I told you like your hydraulic conductivity value, whatever, yeah, your boundary condition to match the observed data with the model simulation using trial and error or an optimization algorithm. So we can do this manually or we can do this using an optimization algorithm. What are the model parameters that we can play with? So that could be the hydraulic conductivity, could be like the shape of the zones or like the value of the zone or whatever, methods that I'm using to estimate my hydraulic conductivity. We generally like creating these zones. This is just one way to represent the hydraulic conductivity, but there are so many other ways for representing hydraulic conductivity. Anisotropy ratio, yeah, between like k in this direction versus k in this direction versus k in this direction. Yeah. Storativity, recharge, boundary conditions. So these are like the model parameter. What is the observation data that my model will try to simulate? Your model, like for a flow model, it could try to simulate hydraulic head, spring discharge, submarine groundwater discharge. So I could measure the spring discharge in the field, and then I will see is my model reproducing the same amount of spring discharge, yes or no. Okay. So again, here is an example. Yeah, calibration history mesh. So let's read this again. Calibration is the process of adjusting the model parameter to match the observation data with the model simulation. Yeah. So in this case, what model parameter? So here is the groundwater flow model. What model parameter did I adjust it here? So I created this model and I adjusted the hydraulic conductivity, just one K value. Yeah. Anisotropy, yeah, anisotropy, like, so that's the second parameter. So I have two parameters here, two boundary condition, like, so the boundary condition here, and I think the boundary condition, so I think it was the boundary condition value here. I raise it up or down, yeah, and so two boundary condition parameter, and I don't know, maybe another one here and one here. I just raise them up and down by factor, yeah, because I don't know their exact value. I know their pattern, how they look like, but I don't know their exact value. So two boundary condition, two fault conductance. So you see here, I have one zone here, and then there is a fault here, and then I have a zone here, and then there is a fault here, and I have another zone here. So the conductance here at this fault and the conductance here at this fault are unknown. So how many parameters do I have? I have one K value, one isotropy value, two boundary condition, so I have 6 parameters. So I keep playing with this 6 parameter, changing this 6 parameter either manually or like using an optimization algorithm until I get a good match between what my model is simulating, which is usually what your model is simulating. You plot it as continuous line because your model is continuous, and what I'm observing in the field. And we usually represent this by dotted line. Why by dotted line? Because this field observation are not continuous. So like you see here, for example, the field observation is only during this period. Here, for example, most of the field observation is during this period, and then few are here. And here, most of them are during this period, and here we have more field observations. These are different monitoring wells. So these are 4 different monitoring well. And how is my model doing? I think my model is doing very good. Like I could simulate this accurately. See, I could get this peak, I could get this peak, I could get this peak. So I could simulate this accurately also here, very accurate here also, here also. So I think my model is doing very good. So the observation and simulated heads. So observed heads, these are the black dot. Simulated heads, this is the blue line. Yeah. So let's look at this model more. Yeah. So here in this model, I was able. Let me go back to here. I was able to get the normalized fitting error only 5%. So the deviation between, like, see here, for example, this is like, let's see this one. WR 102.4, to be. So where is this? That would be like where on this map? It should be somewhere here. Yeah, here. See this one? Oh, like see this well here. I was able to match it very well. Like my model simulation exactly fall on what I'm observing in the field for this monitoring well. So these are different, like, so this is the head, this is the hydraulic head, and this is the time here. So this is the hydraulic head here, this is the time here. And from the period of 75 to 2010, I have a very good match for this observation well. My model can match it very well and so on. Like, let's see here, this one, for example, would be, uh, which one is that? Would be this one, and this one would be like this one. See, have also a good match here, a good match here, so my model can simulate these two. So this model, like this mud flow model, cell size, like each of these cells that you see here is 200 by 200 meter. The model grid, it has zero point 0.4 million cells. It has like 29 layers, so each layer is 93 cell by 178 cell. There are 25 pumping wells. There are 17 observation wells. So 1, 2, 3, 4, 5. If you count this, these are 17 observation well. With how many observation point I have? Like 1,200 data. So you see how many head data was measured. Some of them have condensed data, but some of them has only 2 points. Like you see here, this one has only 2 points, this one has only 2 points, this one has only two, but some of them has very condensed data set. And this is my calibration period from 1975 to 2014. And if you estimate it, like you see like how my model is estimating and what I'm observing, if you count it like the normalizing fitting error is only 5% error. Was like the error between what I'm observing and what I'm simulating is only 5%. How were we able to get such a small error and get this excellent fit between the model with only 6 parameters to play with? Remember I told you we have one K value, one isotropy value, uh, two boundary condition, and two fault conductance. Yeah. So that's like 6 parameter. How was I able to get a good fit with only by changing only 6 parameter? Because I have a rigorous representation of my subsurface. Like I have a high fidelity model. So this is an example of a simple uh, high fidelity simple model. Why high fidelity? Because see, I'm capturing all like the heterogeneity of the aquifer. But why is simple? Because I only have 6 parameters to calibrate. Yeah. Okay. So let's use like here what we will be doing. We will be doing model calibration using best. Uh, so we can do this manually. Like you can go to the your like let's say you run your model and then your model didn't match what you are observing in the field. Then you can manually change the hydraulic conductivity value in this zone. I will say like it's 8, I will make it 10 and then run the model again. Then now I'm getting a better value. Then if it's getting a better value, then I say like maybe change it from 10 to 12. Now I change it to 12, then I get like the value is not as good. Yeah. Then okay, maybe it's between 10 and 12. Let me change it to 11. So you can do this manually, but that's very time consuming. Or you can do it automatically, like using an optimization algorithm. Yeah. And here, that's what Best do. So Best is a software that has like optimization algorithms for calibrating your model. Yeah. So let's read this. Best assist model calibration by varying selecting input of the model. So you basically what you tell him I want to find the best match between my head, this observed head value, and this and their corresponding simulated head value by changing these parameter, by changing hydraulic conductivity, for example, or by changing whatever. Yeah. In your project, I think what you need to do, like you have 6 hydraulic conductivity value, you just tell him find the best match between the simulated and observed head by changing this 6 hydraulic conductivity value. So that the simulated value generated by the model or model mod by the model more closely approach the comparable observed value. So BEST will run the model many times during this process. So basically what BEST will do, it will like suggest like a parameter set. It will test it on the model. If this by a parameter set, I mean like in that case, for example, for your project, the parameter set would be like different k value from k1 to k6. So it will say like I will make k1 like 10, I will make k2 like 50, I will make k3 like 101, I will make k6 like 200, and I'm just making these numbers up. Yeah, it will test this parameter value in the model, and then based on the goodness of the fit, if it like improves the fit between the observed and the simulated, it will make the next decision, like, and select the next parameter set and keep doing this iteratively until it finds a parameter set, like the k value that will give you the best match between what you are simulating and what you are observing. Yeah. Okay. So here model calibration with trial and error. So this is the data that you are observing in the field. Then you design your model, you set up your model, your boundary condition, your geometry, your hydraulic conductivity, your recharge. Then you run your model, you get a model output. Yeah, and then you compare. Yeah, like you compare what you are observing with the model output. So you see here for this point is good, for this point is good, for this point is good. This point you have some error here, this point is good, this point you have some error here. So you compute these errors, yeah, and I will show you how to do this in a minute. Yeah, I will show you like how to compute this error, or how, for example, like here, like I got this error here, like this normalized fitting error. I will show you this in a second. So you compute this error, and then you can say, okay, like to change this one, maybe I will change my hydraulic conductivity field, like how it looks like, or the values of my difference. Or maybe I will change my recharge. Maybe I will change my boundary condition. So you keep playing, you keep changing this until you get like the best fit between what your model is simulating and what you are observing. Okay, so you can do this manually, yeah, or you can get a software to do this for you, to keep changing like these things for you until you get like a good match. Okay, and that would be like automatic calibration using like some codes, for example, are best, some are U code, and this is a modified Gauss-Newton method. Yeah, so this is like a numerical method, for optimization. uh, that solve like a calculate gradients like derivatives, but it calculate the derivatives using a numerical method. Okay, and there are all sorts of uh, of uh, of calibration algorithm out there that you can use. In this case, I will just like it for our case here, like for your project, you will use best. Yeah, and that's what I showed you in the previous video, like how to use best. Okay. But in this video, so in the previous video, you just learned how to use the software. I mean, that's not very important, like how to use the software, because you could be using BEST, you could be using, for example, groundwater modeling system, and groundwater modeling system could have uh, other calibration, optimization algorithm other than BEST, yeah. And it could be also have a different graphical user interface. So each of these graphical user interface, like or calibration software, I mean, you need to learn it. Yeah, once you like, if you're using a new one, you need to learn it. But the basic concept behind any of them will be the same, and that's what I want you to learn in this lesson. Like the basic concept behind, like whether you're using uh, model muse with best, whether you are using GMS with best or other calibration code. I just want you to understand the basic principle behind it. Okay, so Let's look here at how to know, like how could I measure the goodness of fit, like how my model is simulating or reproducing my observation and data. So we what we do, we calculate residual. So residual, that's the difference between the observed and the simulated. So you see here is very small. Here is very small. Here you have some residual. Here you have the largest residual here. Here is very small, and here you have some residual. So you do this, and then you can, like, what do you do with these residuals? So this is called, like, so this is the residual. Yeah, we call residual. So this is the residual, the observed versus the simulated. And remember, like, this Y could be anything. That could be your hydraulic heads. That could be your concentrations. That could be your spring discharge. That could be your submarine groundwater discharge, depending on, on your calibration target. Yeah. Okay. So what do we do with them? Like, how would we know, like, the goodness of it? Like, we just want one number. Yeah. So to get one number, what you can do, you can get like all your residual and you square them. Like, not all your residual, like each of your residual. So you get, like, so this is your residual here. Yeah. And then you square it. Why do you square it? Uh, the reason you square it to get rid of the negative sign, because sometimes if it is like, if you're observe it, if what you are observing, let me show you an example. Yeah. So this is what I am observing. Yeah. Is larger than what I am simulating here. Yeah. Then that would be positive. Yeah. So that is means my model is underestimating. Yeah. But like, let's look at this case here. What I'm observing is less than what I'm simulating. So my model is overestimating here. So that would be like if I calculated the residual. So for this guy, the residual like will be like negative, and for this guy, like the residual will be positive. And if I added them together, they will cancel out. So in order to preventing these two from canceling out, what do? I square the residual, and then after I square them, I take like the square root. Yeah, and then I sum all the residual and take the average. And that is called like root mean square error. And that root mean square error, that basically will tell you that's how the calibration algorithm will do. So your calibration algorithm, it will suggest a parameter set, and then for it will run the model, and for this parameter set, it will calculate the root mean square error, for example, if that's what you selected. And then it will note this number and select another parameter set. And the objective is to find the parameter set that has the smallest like root mean square error. Another metric you can also do to measure the goodness of it, and instead of just taking like you square them and you take the square, like you square them, then take the square roots and take the average, you can just sum all of them. Yeah. So basically I get like the whatever, like again, but you have to square it. Like I get my residual here, I square it, and my residual here, my residual here, my residual square here, my residual square, and I sum all of them. So sum of the squared residual. Uh, Another way, another one, sum of squared residual, weighted residual. Sometimes some of my observation point could be more important than other. Yeah, let me show you an example uh, here. See here, for example, uh, see this is the area of concern. Like here, this is the area of concern where I am most concerned in. So I want this area in my model to be here also to be the most accurate part. Like this is not an area of concern for me. This is not an area of concern for me. This is not an area of concern for me. So my observation here, like these ones here. So you see, these ones are not of a concern for me, and that's why you see like this state agency even didn't get many measurements here. Like, see, these ones are not of concern to me. These are the one of concern to me, and these are the one of concern to me. So what I can do, I can give them a higher weight. Yeah. So that's basically like I could give some uh, points, like some, let's say, like this point, maybe, like, let's say in this example here, I'm more interested not in this early data. I am interested in like this late date after this date. So I can give this one and this one a higher weight here. Yeah. WI could give this one like a higher weight. So even though if I have a higher error here, I don't care. I just want to minimize the error here. I just want to smallest error here. So that's called sum of squared weighted. Like that's how you weight it. Yeah. Okay. Uh, what are the calibration targets that we generally do? Head is the most common. Yeah. So that's the head. That's the most common. Flow rates. Uh, so flow rate, this is important. Like flow rates, that would be like spring discharge or submarine groundwater discharge. Usually, it's not easy to measure something like submarine groundwater discharge. But if you have these measurements and you want to see whether the submarine groundwater discharge that you are measuring in the field, like Earth observation, like field observation, is similar to the ones that your model is simulating, you can also compare this. Concentration, if you're doing a transport model. Travel time and temperature, these are less common. And so if you have a travel time and your model is simulating travel time, then we generally measure travel time in the environment by isotope analysis. Yeah. So these are the state variable or like your decision variable or not decision variable, like these are your state variable or your dependent variable. What is the calibrated variable or like your decision variable or your independent value? This could be parameters like hydraulic conductivity, anisotropy, storativity, dispersivity. Dispersivity, this is related to transport model. We still didn't study this one. Uh, Boundary condition like the boundary flux, the head at the boundary, yeah, depending, or forcing like recharge, yeah. So that could be the calibrated parameter, and you can combine like if you have multiple like let's see here objective function. So this is like we call this like our objective function. So like our this is like called our objective function line. So your objective function could be root mean square error, yeah, and your objective is to minimize this root mean square error or to minimize this SOS or to minimize this SSWE. That's your objective function. So here my objective function, I have like sum of squared weighted residual objective function, but my objective function, it include like head, it include flow, and it include like recharge. So I want like the measured recharge and the measured flow and the measured head in the field to match what my model is reproducing. And from this, you can see that this is an integrated surface water groundwater model. Surface water groundwater model. How this is an integrated surface water groundwater model? Because see, like the model, I'm not the model like recharge is not one of the input for parameter of this model is not one, but it is one of the parameters that my model will simulate. So this model will simulate the head, will simulate flow like spring discharge or submarine groundwater discharge or whatever, and it will also simulate recharge. This means that it's an integrated model. Like so, I just define like the rainfall, I define the ET evapotranspiration, and then it will is my model will simulate recharge. Now, if I'm measuring recharge in the field, then I can compare it with what my model is simulating. Yeah. But here, like, see, this is the head observed versus the head simulated, flow observed versus flow simulated, recharge observed versus recharge simulated. Now, you calibrated your model. After you calibrated your model, you got a figure that looks like this, yeah? So we've seen this in the previous video, but we didn't understand what does this mean or why this is important or how to interpret something like this. So what I did here, I'm just plotting my residual. So I have like for this observation well, this is the residual, the difference between what I observed and what is simulated. And here I have a negative residual about zero point 0.6, like see the minimum. Uh, so the minimum residual is like zero point 0.6. That's very small, like zero point 0.6. That's like 6 centimeter. Yeah, this is a meter, so that's like 6 centimeter. Yeah, negative 6 centimeter, and the maximum is 12 centimeter. Yeah, zero point 0.1 to 12 centimeter. So that's like, see, that is my minimum under estimation, like observed versus simulated, overestimation and underestimation. So means, so like, see, this residual is what, like observed minus simulated. So if the observed, yeah, is larger than the simulated, this means my model is underestimating, yeah. And here this means like, if this means like an overestimating. So here I have an overestimation here, yeah. I have an overestimation here, I have an overestimation here, and then I have underestimation here, underestimation here, and underestimation here for my different observation point. Actually, this looks very good, yeah. Why it looks very good? Because you see my errors are random. So sometimes I'm underestimating, sometimes I'm overestimating, overestimating, underestimating. If all uh, these are like red, like I'm always underestimating, yeah, or all this is blue, like I'm always overestimating, this means that my model has a systematic error. And this means that I need to change something or fix something in my models. Let's say also another case is that like you find part of your model, like this part is all overestimating or underestimating, like all blue, and this part is all red. This is again an indication of a systematic error. The best situation you want to get is something random, is like your residuals are random, you don't see any pattern, and this means that you have random residuals, yeah, or random errors, yeah. So that's basically what you should be getting. Like if you're getting some pattern, this means that there's systematic error in your model. So in your report, I would like to read something like this. The residual is the observed value, measured value in the field minus simulated value, value calculated in the model. Plot of residual on the map of the model area should appear random and show no obvious pattern. Lack of randomness, like residual are all positive in a particular region of the model, can be an indicative of a model error, that your model has a systematic error. So I would like you to like plot the figures that looks like this and shows that, okay, residuals are random, we don't have a systematic error. Another plot we do is this called the 1-1 plot. And this plot, what we do here is that like this is what we observed in the field. So let's say I observed this one. And then I will plot what is the corresponding simulated value. And you see here what I'm observing in the field and what I'm simulating, they are very similar. So they fall on this 1-1 plot. Versus, let's just for the sake of argument, let's say I have like at this point, this is what observed in the field is 105. And what my model is simulating is 107. Yeah, so that would be here, 107. So I would have, so this means that I have a big residual here. Yeah. So I'm observing 105 and I'm simulating like 107, so that would be like a big residual. Okay, but in that case, you see they all fall beautifully on this one-to-one line, which indicates the accuracy of your model. So this is the measured value, and this is the calculated value, and this is the residual. And this is like when how many parameters I kept playing with to get to this value to get to this fitting. 6 hydraulic conductivity parameter. So that's my initial guess for K1. So this K1, this is K2, all the way to K6. That was my initial guess. The model kept playing with these numbers and kept changing them until like, so that's my final model estimate for K1, for K2, for K3, for K4, and so on and so forth. Yeah. And then it will optimize the measurement, the objective function. So the objective function here would be like root mean square error. What does this mean? This means that like if I like see this is my residual, some are positive, some are negative. So if I square this and then take the square root and then take the average of all these guys, I will get this number. And you can do it with Excel. Yeah. So optimize the measure objective function, optimize regularization objective function. Yeah. So that would be like your root mean square error. Yeah. I think that's what we selected for this one. Okay, and you can try it. Like you can get like all these numbers, square them, and then take the square root, uh, takes the average of all the sum of the squared error, and then you will get like this number here. Okay. So for a good fit, the graph points close to the line 1 to 1. But let me show you, like this figure has one problem with it. Like this here has one problem with it, is that like this 1 to 1 line could be misleading. Why? Because let's say this is a big value, yeah? So if it have a big error, it will not appear here because this is a big value. I don't know if that makes sense. Uh, but so there is like this is not like visually like if I have a big error here because just because this is a big value it will not appear here versus here this is like a small value. If I have like even an error that's smaller than here it will appear here because that's a smaller value. So I don't know if you can get this, but so a better figure instead of like you do the simulated versus the observed, a better figure is that like you plot the observed versus the residual, and now that will be it is here I'm plotting the same thing, but here I'm plotting the my simulated value versus the observed value. Here I'm plotting the residual versus the observed value. So now this is the observed value. So for this guy I almost got zero. For this guy, see here, this is my maximum. See, I told you this is my maximum error, like this 12 centimeter. And here, this is my maximum positive error, like 6 centimeter. Yeah, here, this is the 6 centimeter. And this is a 12 centimeter here. So now for each point, now I can see my residual. And that's a good news. Why? If I have a systematic error, I would either have all positive residual or all negative residual. But here some of the residual are positive, some of the residual are negative, so means my residuals are random. So that's like so I want you to do both. I want you like for your modeling report, I want you to show this figure and describe like what does the one-to-one figure mean. And because that's a very like common figure that you will see in many manuscript. But like if you are reviewing a manuscript now, you will tell him don't plot the simulated versus observed, like plot the observed versus simulated. That would be more clearer. And that will show other problems. So let me show you like what problem, like like trends or unequal variance of residual are indicator of model bias. What does this mean? So here, let me show you here. Like, see, this is a one-to-one line. So you look at this. This is the simulated, and this is the observed. And if you are just looking at simulated and versus observed on this like one line, you don't see any problem here. But if you plotted the simulated versus the residual, oh, now we see a problem here. You see like how this is getting larger? So how your variance is getting larger with the simulated value. So this means that this is not a constant variance. So this is a problem here. And that will mean that you need something that you need to fix. Another thing, like you see here, I mean, obviously here, yes, you see some pies here and some pies here, but like once you plot this one, like the residual versus simulated, like instead of the observed versus simulated, then you can exactly see that like as the value increase, there is an upward trend. Yeah, like as the value increase, the residual seem to increase. So here the variance is not constant. So the variance here is a small, the variance here become large, but here there is an upward trend. Okay, so here like small variance and here large variance. I mean, I don't know how much you can understand from this, but uh, again, this is also uh, so this is like there is a statistical term for this. This is called heterostatistic. Heterostatistics means that my variance is not constant. If the like here, see the variance here is kind of constant. Yeah, I mean this could be like an outlier, but here you see the variance increase with the increased value. So my head here was 65. I have a small variance. My head here is 95. I have a large variance. Yeah. And so this is called heterostatistics, and the variance increase as the simulated value increase. Okay, And this can only be seen with the residual versus simulated. I cannot see with one-to-one line. And in this figure, the residual increase as the simulated value increase here. And which is not obvious also from this figure. Okay. So again, I want you also to plot this figure and show me like, okay, the variance is constant and there's no trend for my residual, as in this case, no pies. Okay, so let me just end, like I think that's me end here. Evaluation of the model fit, like graph of residual versus simulated value, graph residual versus simulated value. The two of the requirement for a valid regressions that are residual are random. All residual, the residual have zero mean, like the variance is constant. The residual should be evenly distributed about the zero for all simulated value. Trend or unequal variance are indicator of a model bias. Minimum and maximum residual displays the range of your residuals. So here that's the minimum and maximum. So here that is the maximum and that would be the minimum, the range of your residual. If a model fit is poor, like you don't get like all these line to be on the one-to-one line, or you don't like they don't fall on this line. So if the model fit is poor, you should be cautious. Like, what does this mean? It could mean poor observation. Like, so maybe your model could be more accurate than your data. Like maybe the one who measures this data are in the field is not accurate. Usually the data you get from a state agency like USGS, that's very accurate. Yeah. So, and they will tell you the uncertainty of the data. So they don't just give you the value, they give you the value with uncertainty. It could be also incorrect data interpretation, which led to incorrect like conceptual model. Uh, it could be like data input error. So you need to justify your results. You need to keep updating and improving your model until you get a good fit. If you cannot get a good fit, you can justify your method and like your model limitation. Finally, what I expect you also from the report is that like you will show me the final hydraulic conductivity field, like the final estimate for your hydraulic conductivity value, and the final head after you calibrated the model. So you'll have two figures. One figure would be before you calibrated the model. It will show like these values here, 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 like, and it will show like this head contour. One before calibration and one after calibrating your model. So I think that's all for this video, and I will see you in the next okay. We'll talk about model application. So I leave you here. So for your report, I need two figures. Yeah, one figure uh, before you do the model calibration, show me the hydraulic conductivity field and the head, simulated head, and one figure after you calibrated the model, show me the hydraulic conductivity field and the simulated. Okay. So thank you and see you.